Last segment we talked about, in fact last two segments if you see, we discussed about two special systems of forces. One was about coplanar and the other one was about parallel forces. Now, and then I had mentioned in the last segment that we will be talking about one of the application of the parallel force system, and we have been seeing this I think from your 12th standard or even before that you have been talking about that, and that's the concept of center of mass. Now how that center of mass concept is closely related to the equivalent force system or the simplest resultant of a parallel force system. So that's the topic of this segment. Okay. Now before getting into exactly the derivation of the simplest resultant for such a system, let me first discuss about the main phrase, that is the continuous system, continuous force system. Now what it means is, suppose you have I'll discuss in terms of say 1D, in terms of 2D, and say in terms of 3D. Okay. Now in 1D, what I mean is, suppose you have a line like that. It could be a beam or something. Maybe we are having a beam which is getting represented by a line for simplicity, and on that you have some structure. Means we have built something, maybe of this type, okay. Some construction we have made which is of this type, say, okay, and we are looking at the weight of this. I should have, in fact, what I can do is, okay, the loads I'll just represent by this yellow color maybe, and these are continuous forces. There is no discrete. If you compare this with the discussion which we had in the previous segment, so there we always had forces like a force here and a force there and a couple here, like that, and these forces were acting at a given point, if you remember, if you have noticed. So they were actually acting, a single force acting at a given point. But now at every point we have some force which is acting, and if I go to 2D, maybe there is a surface like that on, say, I'll draw the axis, and this is a surface, 2D surface, okay, and on that you have say loading, which means again, or what I'll do is, better way will be to let's see, first let me draw the axis, and let me say this is x, y and z, and then on this xy plane let me draw the surface, so that it will be much clearer. And then on this surface assume that there is one more distribution of forces. For example, let me draw something like that at the ends like that, and okay, and this is a surface like that, and okay, maybe okay, and at every location you have and then this is sort of like that. So that means on this surface, everywhere we are applying some load. So this orange surface over here, it's sort of the loading. It shows the loading pattern. Then this we will call a 2D continuous. What is this? Okay. Yeah. So this we call a continuous loading on this green surface over here. And now coming to 3D, maybe I'll do this example of, suppose there is a 3D space like that, x, y and z, and on that or in that space we have a 3D body. Okay. And as usual, I'll denote it like this, as I had mentioned in one of the lectures. So this is sort of a 3D body. Okay. And the weight of this, suppose the gravity, and then let me say the gravity is acting downwards. So we can say that at every point in the body there is a pull or the push. In this case, there is a pull from gravity downwards. So and this is happening at every point on the body. Okay. So these are the sort of things which we consider in continuous distribution of forces, where each and every point of my domain, or at least the portion, suppose you consider some portion of the domain of our system, in that domain each and every point is subjected to some force. Okay. That means, in fact, this is very strongly correlated to the concept of continuous function, okay, in maths. So this all these forces, suppose in this 1D, this force, suppose I call this as a force which is a function of x, where x may be in this direction and this side it is f of x. This fx or f of x is actually describing the load. Similarly, in this case, if this is x and y, any point is, say this point will be having a coordinate of x, y, and this, suppose, is again a loading which will be of x, y, function of x, y. This surface, and then the load which is acting on that green surface. And then similarly here, I can't say, means I have to use 4D to actually draw something like that, but you can imagine that every point, suppose the weight I am talking about, it's a function of or density. If I write in terms of, say, density, it's a function of x, y and z, and every location this can change, and based on the density, the force which is acting at that location can be also a function of x, y and z. So these, and then what I was talking about is that these functions are continuous functions in space, in x or in xy or in xyz, at least over a certain range of these parameters, as against here. Okay. Here they were discrete forces. Now here there is a very important point to be observed is all these forces, you have to think of them as, a density functions. It's a very subtle concept, but it needs to be clear, completely clear in your minds. Now why I am saying this is, suppose I ask you that there is a continuous loading like that, you have made a structure on a linear beam like that, and if I ask you what is the load at this point, then what will be your answer? It's like asking that let's come to this. This is the most, I think, intuitive example. Suppose this is the body and this is bothering me. I'll just make it like this to make sure that you understand this is a rigid body. Okay, yeah, fine. So what I was saying, that okay, you consider a body, a point inside this, suppose the point A inside the body, and if I ask you now that what is the mass at that point. Now point is a mathematical definition, you know that it has no volume. So at that point what is the mass? Then in fact it should be 0. Why should there be any mass if the definition of this is a mathematical point? So but then if I tell you to add the mass at all the points, it will not sum up to the total mass of the body if it is say 10 kg. Now so that problem arises whenever you go from a discrete thing to continuous. Another example is suppose I tell you to in probability distribution functions. Okay, now suppose I'll tell you to make 100 chits like that, and you write, these are bad drawings, 1, 2, 3 like that, and you write numbers on them. Okay, say 1, 2, 3 up to 100, and you close your eyes and pick one chit, and if I ask you what is the probability of picking say number 60, so you will tell that the probability is 1 over 100. But then now suppose you make number of chits say 1000, and instead of 1, 2, 3 you write say 0.1, 0.2, 0.3 like that up to 100. So now you have 1000 chits, right? And now if I ask you what's the probability of picking the 60, number 60, you will say 1 over 1000. Now if in this way, if you continue to make a larger and larger number of chits with smaller and smaller gap between them, and if I now and then go to the extreme and where you have infinite number of chits, okay, so that takes you to the continuous pattern. And then if I ask you what's the probability of picking 60, you will say it's 1 over infinity, and it's almost 0, it's 0. But then if you now add all the probabilities, you will end up again something like 0. So it doesn't fit together properly, and to avoid this kind of a misfitting, the concept of density comes into picture. So that is why in this case you won't tell that the probability of picking 60, you tell that probability of picking something near 60. Okay, and that concept will be very clear if you see this. See here you always had a problem to answer the question what is the mass or at point A, but to solve that issue what you did, you defined a density function, okay, which is mass density, and you tell that near the point A, near the mathematical point A, the mass per unit volume is rho. Then if you pick a small volume about A, then suppose that volume is dV, and this rho if you multiply you get this dm. Okay, now because rho is a mathematical function which you can define at every location, there is no problem, and then dV when you multiply you get small dm. Okay, now then the problem is resolved. you can now integrate dm to find out the full mass. And very similar way, actually the probability distribution function, the PDFs are defined so that you can say that probability of say in continuous time, say two friends are planning to meet at a particular location, then what's the probability that they will meet at say 6 p.m. is a very weird question. So the best question is say about 6 p.m. So what's the probability that they will meet between 5:59 and 6:01 p.m. So that's the sort of question which are generally well posed questions. So in this case also, everywhere the function which you will see, they will be functions of densities. Okay, so there will be force means kg per unit length. Here it will be say kg per unit meter square or something, and here you know that it's kg per volume. So that's the density. So in that way, you always should keep in mind that in continuous systems you deal with density functions rather than actual forcing functions. They are force densities rather than forces. Having made that point clear, now we are in a position to come to the concept of the system of that force and how to get the simplest resultant in that case. Okay. Now, just I'll take that example of mass. Let me draw first the body so that I won't have to erase the. So, let's say this is our body and it's a 3D body, and this is our axis maybe. So x, y, z, and this is the body. And now let's have a point somewhere, and near that you pick the small volume whose mass is say dm. Okay. Then let me say the gravity is acting in this z direction. Again, I have chosen my axis so that the z axis matches with the direction of g. Okay. So if you remember the previous discussion about this. Okay. Now, then what will be the force here? So the force here is g times dm, the small force df, right? Now, in fact, again this dm is, we are able to use it because we have defined some continuous function rho, and dm is nothing but rho dv sort of thing. Okay. And this is that continuous function which we have defined to define the mass density over this volume. Anyways, so and now if you pick any such points, say this is point A and maybe point B here, if you pick a volume, again the same sort of force will act, and all these forces at every location will be acting downwards. So is it not very similar to the case of the parallel force system which we discussed in the previous segment? So that means we can just write that the total force, say Fr, F resultant, that's what we had used, will be what we had summed it up. If you remember, we had taken all the forces to the z axis and we just summed them up. Now in this case, summing is like integration because it's a continuous system, and so we can write what, that say at every location, so rho dv into g, so this is dm, and I'll just integrate, and then in fact this is to be, what would I do, I can be more explicit, to write this as a function of x, y, yeah, z or something, and dv. Okay. So, and then this will be, this force will be in what direction? So, g, in fact, it's a vector. So, this will be, g times k, like this I can always write. So, then I can write so here minus times k, if I want to write in the vector form, because we have been doing it with everything with vectors, so it's better to write in this way. Okay. So now if you add all these things, so you will get in a way the whole mass of the body times g times k, negative direction. Is that fine? Okay. So that's what you will get in a way. Now, so this is what the summation of all the forces happened. But now we said that the simplest resultant would be that because we can remove that one couple moment will come because we have moved all these forces to that location. But then to cancel out that that couple moment, we said that we can move the force so that will be cancelled out, right? So, the same thing we will do. Let us say we have moved that resultant Fr to a location somewhere here, maybe, which is acting like this. Okay, a bold one I had drawn there. So, bold one I will draw here. Okay. So, this is like your Fr. I have moved it to a location which I will somehow say this is the location maybe, and this let me call this as say x with a bar and y with a bar. Okay. So, that means this distance here is, so this distance is y barred and this is x with a bar. Okay. So, that means now the moment of this force about x and y should be the same as it was earlier when we had not summed them up, clubbed them up, right. So, that equation, how would I write? Say suppose I am taking the moment about say x, then what it would be? So, F, I will use say the yellow color only. Now, Fr times, okay, I am using just the magnitude now, times y, right. So, about this x axis is equal to integral of what? All the forces which would have, let me say this. So, x times, so g will be always there, times rho dv, but then there will be an x at every location, right. So, that is the small mass dm. So, dm times g is df, but it is acting at a given x because rho is a function of x, y, z, and so what should be? Should it be x or y? Because we are taking the moment about this, so y coordinate, right? So I'll sorry for that. So this is not the one. We should have y, right? So that means your y coordinate of this location where the line of action of Fr should pass will be given by g integral y rho dv over this fr. Fr is nothing but this full thing. Okay. Is that fine? Or if you want to write in terms of mass, what will happen is this g also will get cancelled out. So this g will get cancelled out with this, and you will have y rho dv over m. Fine? And in the exactly in the same way, so this is okay. I'll write it as a summary somewhere. Okay. So now y bar has come out to be integral of y rho dv over m, and arguing in the exactly same way, just replacing y bar here with x bar and y here with x, we can write that, say, x bar will be integral of x rho dv over m. Now this is, what you have already known as the center of mass of this body. So that means if I'll just come to the word center of mass before the so now this resultant force is passing through a line of action which whose x bar and y bar coordinates are like this. Now if I turn this body, okay, now then what will happen is, let me go to the another one. It is just a suppose you have the axis like this, sorry. So you have the axis like this, and suppose initially your body was like this, and you created that Fr force, and from that you have, suppose you created this line, okay, and then what you do, you twist the body into another orientation, and then what you will get is another line. So maybe I'll show that line as this one, and if you keep on turning this body to different orientation, always this vertical line means, so please understand what these lines mean. Now in this orientation, this particular line is moving through this, and similarly if you turn this, so that line will move like that. So if you join all those lines will move through a single point, and that point we call it as the center of mass. But the concept of that center of mass is coming from the simplest resultant of all these parallel forces which are acting, and you are creating the simplest resultant by keeping the equivalence of the effect, both the force type and the moment type. So this is the force equivalence, and this is coming from the moment equivalence, because we have taken in such a way that in about z axis there is no moment of these forces. So we have just this is about the x axis, and if you take the moment about the y axis, you will okay, yeah, it was slightly stopped. Yeah. So if you see this, if you consider the moment about the x axis, you will get yeah, this equation, that is this, and if you consider the moment about y axis, you will get this equation. And so that is what I was talking about, that considering the parallel force systems, the concept of center of mass becomes much more clearer, or you get at least another viewpoint to look at the center of mass and how it works. So then one more very similar concept is, I'll just move this around a bit. Suppose you have a surface like this on, say, the xy plane, okay, xyz, and then there is some surface here, okay, and imagine that you have some pressure field which is acting here, okay, at every location. So they are not discrete forces, but there is a continuous pressure field which is acting here, okay, like the one I had discussed in the first slide. Now then this full pressure field can be thought of or replaced with as a single force somewhere, right? Now that and the effect will be effect of what? The total force and the couple moment which is acting about both x and y. That's exactly the same way what we did. Now that replacement, when you do, suppose I make it with this. So this, if you make that, this is the force which is acting. So this point here is called the center of the pressure, okay, as if the full thing you have just got rid of, and you are saying that okay, a single force which is equivalent to the complete pressure field is acting at that location, and the location where you have to apply that force, so that the force as well as the moment will remain exactly the same as with the original case. So that location will be called the center of pressure. Yeah, so these are the two very interesting application of the parallel force systems. So I thought they deserve one separate segment for their discussion. So we will see in the next segment the most general system of forces and what will be its simplest resultant when we figure out. See you in the next segment.